Is it audible, sir? Your voice is clear here.
Okay, good. I just wanted to make sure. All right, let's do question 6 if you have no questions on this one. This one is now we have to start applying what we have learned in a new concept. So the question says that you have a waveguide which consists of a semicircular cross section. So basically the waveguide is semicircular. So instead of being a full circular, it is semicircular. This is 0 and the radius is A. And you are asked to calculate the appropriate expression for the longitudinal component of the electric field of the TM mode. I'll solve this A part. I'll solve C part. I'll keep B part for you to try on your own once we have solved A and C. And you can think about the parts there. So again, it's a waveguide which is semicircular in its nature, and you have to calculate the longitudinal component of the electric field for the TM mode. So again, we are looking for a mode which has a component in the Z direction. So the component is Ez, and obviously this component is going to vary in R and phi. These are the terms I'm looking for. Now remember, when we were doing for a full circular waveguide, our electric field E had to be the same when phi became 2 pi as it was at phi is equal to 0. That was the condition we had created, that it had to be the same, and thus I had to create cos m phi term in there. Now the condition has changed. Now basically you have a semicircular waveguide. Everything which is red is a conductor. So when I have the electric field at phi is equal to 0, so when the electric field is happening at this term over here, when phi is equal to 0, this electric field is going to be hitting this conductor perpendicularly and is going to be tangential to the bottom conductor. Because this electric field is tangential to the bottom conductor, this electric field E at phi is equal to 0 has to be 0. Anywhere I go from 0 to A, when phi is 0, the electric field has to be 0. And similarly, when I go to phi is equal to pi, E has to be 0 here too. So this Ez component which we are talking about has to be 0 when phi is equal to 0, because the electric field is now parallel to the conductor boundary at the bottom, and has to be 0 when phi is equal to pi. We know that this field is basically looking at this field. This equation is still true, d square d phi square plus m square phi is equal to 0. That hasn't changed at all. So we know that Ez or phi function has to be of the order of a cos m phi plus b sin m phi. Has to be of that order. This part hasn't changed. This part remains the same as your circular waveguide. When we were deriving this, we hadn't put any boundary conditions. That equation is independent of the boundary conditions. It's when we put the boundary conditions we start to look at the various things. So because at phi is equal to 0, my phi variation of the function has to be 0. It tells me my a has to be 0. So the variation in phi, the independent variable in phi, would have to be of the order of sine m phi. And at phi is equal to pi, again this function has to be 0. So it's telling you sine m pi has to be 0. Therefore, m has to be an integer. However, m cannot be 0. Because if m is 0, this function goes to 0 and nothing happens. There's no electric field present. This is where it is different from the circular waveguide. In the circular waveguide, the lowest order term could be 0. However, here the lowest order term cannot be 0. Remember again in the circular term when we were looking at the mode TM010 mode, then there was no variation happening in phi at all. However, in the semicircular waveguide, there would be a variation happening in the phi direction, and at minimum the variation would be 1. So Ez would again be of the form of a Bessel function of order m with arguments hr sine m phi with e minus j beta z z. That would be the function for Ez for the Tm mode. However, in this specific case, m has to be between 1, 2, 3, so forth and so on. So this function you look at is is a function where Ez is 0 at r is equal to 0. Remember, it's only for the J0 function, only for the zeroth order of the Bessel function of first kind is there an amplitude at r is equal to 0. So this is a function where basically the electric field will have to be 0 at r is equal to 0, and around that the electric field would change. But that's what the answer would be. If I was going to look at how I would solve the problem for the C part, how would I look for the mode, which mode exists and which mode is the smallest mode, smallest dominant Tm mode. What is that value? Well, for the dominant Tm mode, I have to have Jm Ha has to be 0 and m has to be equal to 1. That would be the lowest terms. So it's telling you J1 Ha has to be 0, and thus what would happen is I have to go to the first 0 of J1 function. which is at 3.832. So HA has to be 3.832 or H has to be 3.832 by A, and this is going to be TM11 mode. So I would see my dominant mode, TM mode, is going to be TM11. The first function is telling you that there is one half lambda fitting in the phi direction, m is equal to 1, and because of that the order of the function is 1, which means that there is no electric field in the center r is equal to 0, but there is uh, and then I'm going to the first root of that function in the Bessel form. So that's how the solution is going to look like for the TM mode. Next, like now you should practice what is going to, so I gave you the TM mode solution. Next you can basically look at what would the TE mode look like. And what you have to think for the TE mode is instead of HZ, you're going to have EZ, you're going to have an HZ R phi function. So go through this exercise again. Go through this exercise and see what would happen. Again, the variation in phi direction would remain the same, but remember HZ is parallel to the boundary condition at phi is equal to 0 and parallel to the boundary condition at phi is equal to pi. So you'll have to think of what that function should look like. Is it going to be 0 at that value, or is it going to be maximum at that value? So think of that, whether you'll get a sine function or a cosine function, and then think of what roots would you have to be looking for. Would you have to be looking for the roots of J1 function, or would you have to be looking for the roots of J1 prime function, the derivative of J1 function? So think about that, and that's how you would get to the TE mode. Any questions on this?
Sir, in center one, they don't have any doubt. We move to the next problem, sir.
Okay.
So is it audible?
Yes, it's quite audible to me. All right, let's move to the next problem, which is question 7. It basically says a waveguide resonator with air-filled cavity has dimensions of 8 centimeters, 6 centimeters, and 5 centimeters. Let's just say A is equal to 8 centimeters, B is equal to 6 centimeters, C is equal to 5 centimeters. The question is asking you to find the first 12 lowest order modes and their resonant frequencies. So because you have 12 modes, we can't just keep on calculating every single thing. We want to get down to some numbers very, very quickly. And then for certain cases, we will have to calculate. There's no ifs or buts about it. There are about 4 or 5 modes we should be able to do very, very quickly. After that, we should start calculating stuff. Because again, remember the resonant frequency FR is given by 1 by 2 pi square root of mu epsilon square root of m pi by a square plus n pi by b square plus p pi by c square. And I can make it simpler. It basically says this is an air-filled cavity, so mu has to be equal to mu naught, epsilon has to be equal to epsilon naught, and then this 1 by square root of mu epsilon is nothing but c by 2, and this pi will cancel out these pi's on the front, so it just becomes c by 2 square root of m by a square plus n by b square plus p by c square, where m, n, and p are the various values of the subscript. Again, a is greater than b is greater than c, so we need to do 1 by a is less than 1 by b is less than 1 by c. These are the combinations I have to be doing. And in the resonance frequency, you basically see the terms which are showing up there. And if you want, you can say 1 by a square is less than 1 by b square is less than 1 by c square. And you can, I would suggest, put the values of 1 by a square. So 1 by 8 square, 1 by 6 square, 1 by 5 square. You can put these values and you can get a relative value of each of these terms. So to look at the modes now, again, 1 by b square, one by c square. Let's make a table and see what these modes could possibly be. So we have the modes, what modes are present, and obviously, again, remember, when in a resonant cavity, few rules apply. Let's look at some of the rules. Few rules which apply are, at most, one of m, n, and p can be 0. We can't have more than one which is 0. For Tm mode, m and n cannot be 0. For Te mode, p cannot be 0. So we can now start looking at the combinations of the subscripts. At least two of these terms have to exist. So obviously, because the terms are existing, obviously we want the lowest order modes would be when value of the two subscripts would be 0. The first term which would be lowest would be 1, 1, 0. When I combine these two terms, when I add 1 plus a square plus 1 by b square, that's why just putting the values of 1 by a square would be good too, versus 1 by b square. And then the second term would be 1 by a square is the smallest. To that, I add the next highest term, which is 1 by c square. So this should be 1, 0, 1. And then I should add 1 by b square and 1 by and then combinations of all three, 1, 1, 1. So these four things I should be able to, I know very quickly they would be the lowest terms. 1, 1, 0 when I combine 1 by a square and 1 by b square, 1 by a square and 1 by c square, and then 1 by b square and 1 by c square. The first mode, which is TE, which is 1, 1, 0, has p is equal to 0, so this mode can only be a TM mode. The second mode has n is equal to 0, so this can only be a TE mode. The third one has m is equal to 0, so this can only be a TE mode. The fourth mode has allowed, so that has to be TE 111 or TM 111. If you substitute the terms, just do the mathematical algebra, just do the mathematical arithmetics. This turns out to be 3.125 gigahertz. This turns out to be 3.538 gigahertz, 3.905 gigahertz, and this is 4.332 gigahertz. Now you basically have to start combining the higher order terms. So instead of one of the terms has to become 2 and the remaining terms should be 1. So the next one would be T210. Smallest term go to 2, making the smallest term go to 2, making the next term go to making the next term go to 1. So one time I have hello. So one time I have basically converted the 1 by a square into 2 and this into 1, and the other time I'm adding the 1 by c square term to it too. Again, p is equal to 0, so this can only be a TM mode. N is equal to 0, so this can only be a TE mode. Substituting the values, you'll get 4.802 gigahertz and 5.340 gigahertz. The next term, which turns out to be true now, is I make b go to 0 and I add a to it, so I get 1 to 0. And again, p is 0, so this can only be a TM mode, and this value would be 5.414 gigahertz. So far I've counted 1, 2, 3, 4, 5, 6, 7, 8 modes. The next highest mode is not actually 0 to 1, what you would expect, but is 2, 1, 1. So this is the place, once you get down to the bottom places, this is the place where you have to start doing some simple calculations. Just keep on adding 2 times 1 by a square, 1 times 1 by b square, and find out which is the next closest one. The next term is 2, 1, 1, and after that is 0, 2, 1, and after that it is 1, 2, 1. 2, 1, 1 is going to be both TE or TM. 0 to 1 can only be TE. 1 to 1 is both TE and TM. And if you put the values, you get 5.731 gigahertz and you get 6.125 gigahertz. So anytime you have these kind of problems where you are asked to find a certain number of modes, a good thing would be to calculate the value of 1 by a square, a value of 1 by b square, and a value of 1 by c square. And normally for the first 4 modes or 5 modes, these terms would be the ones which will always be the first 5 terms. After that, sometimes you'll have to figure out the combinations. But you can easily do it if you know the values of 1 by a square. You're just doing the summations then. And you can find out which summation is highest or lowest. Sometimes just to make our life easier, we sometimes call this factor to be F factor, capital F factor, FMNP factor, so that FR is C by 2 of FMNP. And then you can quickly calculate these factors with once you have so my suggestion would always be calculate this term, and calculate the third term, and then just keep on adding the different subscript values of those, and arranging those subscript values according to their ascending order. Questions on the problem? Any questions on the problem?
No questions, sir. Yeah, no questions.
No questions. Okay. All right, let's go to the next problem again. An easy problem per se, not that difficult. An air-filled rectangular cavity with brass walls has dimensions 4 centimeters by 3 centimeters by 5 centimeters. So we know A is equal to 4 centimeters, B is equal to 3 centimeters, C is equal to 5 centimeters. So you see C is greater than A is greater than B, or 1 by C square is less than 1 by A square is less than 1 by B square. As soon as you start seeing dimensions, you should start thinking about which combinations would work. Determine the dominant mode and its resonant frequency for the cavity. So for the dominant mode, again remember the rules, 2 rules, only one of M, N or P could be 0, and then the rules of TE or TM. So it's telling me, because this is the conduction, I should have this go to 1, so P should be 1, M should be 1, and N should be 0. So I have the combination of 1, 0, 1. That's the combination which will give me the lowest frequency. That gives me the lowest resonant frequency. Again, in this case, N is equal to 0, so can't be a TM mode. So the mode 0, 1 mode Hello, can you hear me? So the mode has to be TE101 mode, and F101, we just did the calculations, was C by 2 square root of 1 by A square plus 1 by C square, C being the speed of light and that being the other C. So let's call it U, speed of light. And this would be 4.802 gigahertz. Q for a resonant cavity is pi resonant frequency by Rs mu naught A B C A square plus C square divided by 2B A cube plus C cube plus AC A square plus C square. And your Rs is pi mu naught F by sigma, which has been given to you. So Q, when you substitute the values, will turn out to be 6869. The next question which asks is calculate the resonant energy, and I think there is something missing here. Calculate the time average stored electric and magnetic energies of the resonant frequency. So the value of H naught is not given. Value of H naught is not there. So we can define it in terms of H naught terms. Let's assume H naught for the time being is 0.01 amperes per meter, or you can define it in H naught terms. 4 epsilon WM would be the same, exactly that. You don't need to redo any calculations. Any questions?
No questions.
You can hear me still?
Yes, sir, we can hear you.
Okay. Just a second. I'm just saving this file for a second. All right. Let's do the next question. This question is a question where we have to understand maths well to make our life easy without having to do difficult calculations. The question is saying that you have a rectangular cavity of length d. I should mention here that when you look at different books, some books use length to be c, some books use length to be d. I think I realized why length d is better, because c also shows up at speed of light and people can get confused. So maybe we could use d. Anyway, but anytime if you see D being used in any books, it's basically what we have used as C in the class. Rectangular cavity of resonant length D is to be constructed from an A by B rectangular waveguide, and it has to be operated at TE101 mode. For a fixed value of B, you don't change the value of B, the value of B remains fixed. Determine the relative magnitude of A and D, there should be D here, such that the cavity length, cavity Q is maximized. That's what this basically is asking you to do. Well, it is TE101 mode, and we know that the TE10 mode, the resonant frequency FR is going to be given by C by 2, C being the speed of light, and 1 by A square plus 1 by D square. And I can write this as C by 2 square root of D square plus A square divided by A square D square, or C by 2AD square root of A square plus D square. So Q, as we had derived in the class, was pi F101 mu naught ABD A square plus D square by RS 2B A cube plus D cube plus AD A square plus D square. We can substitute the value of F101 in there. Again, remember, F resonant frequency is dependent upon both A and D's. And this is what we are trying to maximize. So when we substitute it, basically we end up getting a term which is pi C mu naught by 2RS B A square plus D square 3 by 2. So I have A square plus D square from here, and I have half from there, so 3 by 2. And I have this AD cancel with this AD over here, so that goes away, divided by 2B A cube plus D cube plus AD A square plus D square. And even RS term has the frequency component in it. The RS term is pi mu naught F by sigma, and the F term is the frequency term I have. So you can put that value in there too. However, let's look at this function now. Let's look at this function Q. Pi by 2RS mu naught B A square plus D square 3 by 2 2B A cube plus D cube plus AD A square plus D square. And the goal is to maximize this function. To maximize that value. And normally in engineering, what you want to maximize a function, you have to take the derivative of the function with a variable you're trying to maximize. In this case, you're trying to maximize the function for the ratio of D by A. Right? You want to you have a fixed b, you have some a, you want to figure out what should the value of d be with respect to a for me to get a maximum term, a maximum value of q. And again, you can put the value of rs too. The argument which I'm going to make is still going to be true when you put the value of rs. You basically are getting a term in a and d's. I'm saying that I don't really need to do the derivatives. I have to just think about this problem and I should get to the answer with very, very quickly. The derivative is going to be really, really complex here. I mean, it's going to spend a lot of time doing it. But what you notice here very quickly is that q function, even when you put the value of rs, q function is symmetric to a and d. Whatever is the value of a term is the values of terms you're getting there. If I called d to be a, and a to be d, nothing changes. This function is completely symmetric to these two terms, a and these terms. If I swap a and d's, the function doesn't change at all. Obviously, the minimum of the function will happen when either of the two terms are zeros. So I know that the minimum is very clear. So the way, if the function, when I'm swapping the two variables and the function doesn't change, then the only way I would get maxima in that function would be when the two terms are equal. So because this function is symmetric to an a and b, the maxima would be maximum q will be when a is equal to d. Otherwise, if you do it here, you do the derivative here, you do all the calculations there, and you get some ratio r between d and a, and that ratio is not 1, then when you swap the value of a and d and you do the calculations again, you should get a different answer, which makes absolutely no sense because the function is symmetric. The function hasn't really changed. The value should not really change. So the maximum should be when a is equal to d. So the answer of the a part is going to be that it's going to be maximum when a is equal to d, and that maximum is going to be, so then you can substitute the value of a and d to calculate what the value of q would be. I think the second part is obtain an expression of q as a function of a by b under these conditions. So you just substitute the value of a. So basically you get pi c by 2rs mu naught b 2a square 3 by 2 by 2b 2a cube plus a square 2a square, and this becomes a cube, and then you have to substitute the value of rs2 in terms of frequency, and you should be able to get to your answer. You should be able to get the value of q in the term. I wouldn't do it, but that is pretty trivial to do afterwards. So what you have to realize to make this problem easy is that this function here is symmetric in a and d. So if I put this to be a and d and I did the derivative and I made the derivative go to 0 and then basically got some answer of the ratio. If that ratio is not equal to 1, if I swap the two variables, then then when I do the derivative, my ratio would be 1 by r prime. So basically the question is, if I choose AD, if I choose A and D and get ratio of R, whatever the value of R be, then I swap A prime to be D and D prime to be A. The ratio I will be 1 by R, but the function hasn't changed. So R should be equal to 1 by R, or R should be equal to 1. Questions? So sometimes you need to look at the symmetry of the functions, because that makes your problem so much easier to solve. Any questions on this?
No questions, sir.
Is this concept clear? Like fully clear, right?
Yes, sir.
All right. Hopefully I taught you another mathematical trick to look for maximas in the problem. All right, let's go to the next question then. Question 11. And question 11 is, you have an air-filled rectangular cavity which basically is telling you mu is mu naught, epsilon is epsilon naught, and phase velocity is c. You have to calculate its q for TE10 mode if its dimensions are given to you as that A is equal to C is equal to B. Next question is, determine how much A and B should be increased in order to make Q 20% larger. So the first part is Q is, I'm looking at Q101, and that would be given by, I'm substituting the value of RS here too now. So it will be pi F101 mu naught sigma A B C A square plus C square to be, well, let's call it D, to be A cube plus D cube plus AD A square plus D square. A is equal to C is equal to A is equal to, let's call this D just so that we don't confuse with speed of light, is equal to 1.8 B is equal to 3.6 centimeters. F101 is going to be speed of light by 2. Just speed of, it's going through a material of speed of light, 1 by A square plus 1 by D square. And when you substitute, this is going to be 0.1179 gigahertz. So if I now substitute these terms in, Q101 is going to be given by, let's substitute the various terms in. It's going to be given by, obviously it'll depend, we can put all these values over here. It'll depend upon square root of sigma. And my next question is, how much should A and B be increased so that the Q becomes, in order to make the Q 20% larger, and A is equal to D. So I want to keep the expression of B within that region. I don't want to change the expression of B because I want to see what happens in the next term to look for various things. Is something missing in my calculation? Just a second, there is something missing in my calculation which I'm not sure. Just a second, let me, I'm missing something in my calculation. Give me like 2 minutes to look through the equation and I will get back to you. Just a I'm just looking through the equation in the class. Oh yeah, I found the mistake, sorry. Yeah. Alright, yes, I found the mistake I have done. I'll correct it right now and we'll solve it. Let me go to a new page. I'm going to do that again. And basically, the solution is Q101. Substituting the value of RS, we have it as pi square root of F01 mu naught sigma ABC A square plus ABD A square plus D square divided by 2B A cube plus D cube plus AD A square plus D square. And I have A is equal to D is equal to 1.8B, and the term is 3.6 centimeters, but I don't really want to look at that. I want to get an expression of Q in terms of A's and B's. And remember again that A is equal to D gives me maximum Q. We just did that problem. Gives me maximum value of Q when A is equal to D. So what I want to do is I want to calculate the value of, my next part is asking me, my part B is asking me that I want to determine how much A and B should be increased in order to make Q 20% larger. So what I want to really understand in first part, if I look at the second part and try to solve the problem, is Q as a function of A or B. Under the condition that A is equal to 1.8B, I want to basically understand what is the value of Q under those conditions. So to do that, what I'm going to do is I'm going to substitute the values of A and D. Instead of calling it 3.6 centimeters, I'm going to first substitute the values of A and D's in terms of B's within my relationships over here, so that I get Q101 as a function of B. So I don't want to substitute the exact value of 3.6 centimeter which has been given to me, but keep it in the relationship of B, because that's what I would need to know of how to solve my second part. Otherwise, I'm lost in the second part. So again, F101 we know is C by 2 square root of 1 by A square plus 1 by D square. But A is equal to D, so that is C by 2 square root of 2A square, or C by square root of 2 1 by A. But A is 1 by 0.8B, so I can write this as C by square root of 2 1.8 into 1 by B. So I'm going to turn everything into B's instead of turn, or you can, if you don't like that, you can turn everything into A's. You can keep this over here, and then you can, wherever B is present, you can convert B into A by 1.8. So F101 is 1.179 into 10 to power 8 by B, meters per second, hertz. So I substitute these terms. So I substitute this relationship everywhere here, and I substitute F right over there. You basically will see F101 has a square root of, has basically every other term, the B terms will start cancelling each other out. But F101, you have a square root of B, 1 by square root of B term here, and then you have a B term over here. On the top and the bottom, you basically have the same orders, A square into AD, A to the power 4, B into A cube, A to the power 4. So B to the power 4 terms will go away there. B to the power 4 terms will go away. And similarly, here you have to the power 4 terms. So what is basically left is 1 by square root of B from here, 1 by square root of B from here, and a B from there. So you should know that. Now you should know Q101 should be proportional to 1 by square root of B into B. So should be proportional to square root of B. If you substitute all these values, you'll get Q101 is equal to 10.22 square root of sigma B. And you can substitute the values of sigma and other terms and get whatever you want to get. The second part asks that I want to create a cavity where Q prime 101 is equal to 20% higher, so 1.2 times Q101. I want to create a new cavity, 20% higher Q. It should be equal to 101, but Q depends upon B, square root of B, therefore B prime should be 1.2 square of B, because it depends on B prime, it should be that. So this should be 1.44 B. So the cavity dimensions have to increase by 44%. That's where you would get the maximum term. So again, as engineers, normally, you can substitute the values directly in here, but when you substitute the terms directly in, you do not get a feel of what is happening. So as engineers, we should always try to first do things in variables and try to simplify the variables so that we can start getting a feel of what's happening, and then we can substitute the values, because then you would know whether you're doing things right or wrong. So, any questions?
So can you hear me?
Yes, I can hear you.
So in rectangular waveguides, we have a standard rectangular waveguide having a dimension of B is equal to A by 2. The same way in cavity resonator, do we have any standard resonator dimensions?
No, we don't have any specific standard resonator dimensions per se, except normally we would like to keep A is equal to D. The length, the length and one of the cavities to be same. And then basically it depends upon your resonant frequency, what resonant frequency that you want to use that. Dimensions would normally be determined by those resonant frequencies. For waveguides, we had not a standard but a good thumb rule that B is equal to A by 2, because that provides you the lowest loss while providing you a decent bandwidth. And in that case, you have a propagating wave. So if my B becomes larger, if my B approaches the value of A, my loss becomes very, very good. But if my B is much, uh, uh, if my B approaches A, my loss decreases, but my bandwidth, my second order mode system mode bandwidth decreases too. So that is normally the consideration in a waveguide, that you have two competing arguments that are going around. One is you want the loss to be minimum, but you also want to have the bandwidth to be as large as possible for the propagating mode. In a resonating cavity, you would have a propagating mode. So normally you don't like A is equal to B. You do not like the terms. You don't normally the resonating cavity. And this part here. Uh, you do not like A is equal to B is equal to D, because this is three degenerate modes. The three degenerate modes are basically your TM110, TE101, and TE102. 0, 1, 1. These three modes are degenerate, so you do not like that conditions. But A is equal to D provides, this one provides the, this one provides you the highest Q for a given value of B. And this one only is basically supporting T101 mode, is the dominant mode. Then the ratio between A and D is normally decided based both on the how much you need, how much resonance you need, and what value of Q you need. But there are no specific guidelines for that, like a waveguide. Waveguide, you basically have two competing problems, so it's easy to create a guideline. Here, you normally just go with your feeling. Again, these are degenerate modes. You are exciting these modes very specifically, but that's an ideal condition. So in principle, I can excite only one of those two modes by the right design of the probes. However, that is assuming that there is no roughness on the metals. The metals are nice and smooth. In reality, there would always be some roughness on the metals. There would always be some rounding of the corners. So some of that energy would be lost to the other resonating mode. And in principle, they would be expected to be degenerate, but in reality, they would be slightly off in frequency, very, very slightly off in frequency. So it's not a practically good solution to go for A is equal to B is equal to D. But A is equal to D still provides you a single mode, TE101 mode as we have defined it. But then B value, there's no specific guideline for designing B values. It's just you just sit and you simulate the Q values and you basically uh, uh, you basically it is determined. Your A value is normally your A value is now fixed by your resonant frequency. If I'm going for TE101 mode, and I want a specific frequency of, let's say, resonant frequency of 10 gigahertz, then my A value is automatically determined. And then you go for the B values, uh, change the B values around, you see which gives you the highest Q while providing you a decent, which gives you the highest Q basically. But you don't want it to be equal to D, so you normally have it larger than A and D's. Did I answer your question or
Yes, sir. Yes, sir.
somewhat, right? Okay. Any other questions?
No, sir. No questions.
Sorry. Yeah, I mean, if you look at question 17, then that would be the dominant resonant designer cubical resonant cavity with a dominant frequency of 5.6 gigahertz. So that basically goes like as soon as the that's a very easy problem. I think you should be able to solve it. A is equal to B is equal to C. And then look at it. All right. I think it's time to stop. I don't know whether I don't have any other questions from this assignment. But I've done most of the hard questions on this assignment. What I would like you to do is we solve the TEM mode for the circular waveguide, semicircular waveguide. If you look at the TE mode for the semicircular waveguide. But beyond that, I've done most of the hard questions in this assignment. Any questions? Otherwise, we can meet tomorrow. We'll look at questions from assignment 1 and assignment 2 tomorrow.
Yeah, Krishna, have any questions? Shall we wind up?
Okay, let's wind up then.
Yes, sir. We'll write that.
So we'll do questions from assignment 1 and 2 tomorrow then. Tomorrow is the last class or is it on?
Yes, sir. Tomorrow is the last class, sir.
Okay. So again, have the students go through those questions beforehand. And if there's any specific question they want to bring over, we can discuss that. But I'll pick up the most hard questions in those assignments and we'll go over those questions.
Okay, sir.
All right. All right. Then, see you guys tomorrow.